of the course, Silicon Micro Ring Resonators, its application in optical computing.
Thank you. Actually, so I do have two topics, and so you have to choose whether I have to talk about the use of silicon. Since tomorrow we will start to talk about quantum photonics, and therefore now I have two topics. One is the application of micro-ring resonator in optical computing, so neuromorphic computing, brain-inspired computing. And the other one is to use the silicon photonics in optical networking. So what do you want to hear about? So those who want to know about optical computing, raise hands. No one. Okay. One. Okay, good. Thank you. Those who want to know about use of silicon photonics in optical networking, raise hands. Okay, optical networking then. Okay. And so here is the use of silicon photonics, and what I want to tell you is the application in on-chip optical networking, okay? So what I'm going to do is that really I'm trying to go through all the different steps, all the different components that we have developed in order to make an optical network on chip. And for that, I need to acknowledge the people that in the lab did this work. So Mattia Mancinelli, Stefano Tondini, Claudio Castellan, and Astrid Chailan. So she's the sister of Tate. And so the question, so the reason why we have started this project is because of data center. And in data center, you have 1,000 or million of servers that are connected with 1,000 of fibers. And one aspect that people do not really realize is the fact that when you are shown a picture of a data center, so typically they do show you the servers, okay? And here is the server. But then if you look in the basement, so what you see in the basement is a huge amount of pipelines that are indeed used in order to cool down all the servers, so in order to dissipate all the power that is developed in the server. And therefore, there is a huge motivation in order to substitute and in order to make these networks, so the transfer of data within the data center, more effective. And indeed, in the past, so we have, together with Francesco Testa, so we have edited this book that is about the use of optics in order to switch, in order to route the signal in data centers, okay? So here the motivation of the work that I'm going to introduce you is associated to the fact that in optical communications, so you have nodes. And what you need to have is that those nodes need to be reconfigurable, meaning that you want to connect any direction with any direction in a easy and reconfigurable manner. And nowadays, the technology to do this switching, this reconfiguration of the network is essentially based on microelectronic mechanical systems. So they are very effective, even though they are costly and they are massive, they are large. And what is even more problematic from our point of view is that the time they take to reconfigure the system is quite long. So it's in the order of a few milliseconds. And the reason why the time is so long is because you need careful alignment. So in one of these MEMS-based systems where you have many fibers, so the key component is the rerouting of the optical signal. So what you have is that you have a mirror, which is actuated by our MEMS. So the MEMS are moving the face of the mirror. And this movement can be quite fast because the mirrors are quite small. So It can happen on a gigahertz rate. However, what happens is that you need to very carefully align. So in this situation, for example, you have a fiber input here that the light is propagating in free space, is reaching this mirror, MEMS mirror here, that other MEMS mirror there, and then the light is steered exactly on the proper output. And so in this way, you can decide either to send the output here or to send the output there. And so in this way, you reconfigure the network. However, so the time to switch from one port to the other port is a few milliseconds. And the reason why is a few milliseconds is because now you need to control the mirrors in a very precise way in order to really align the light output to the proper fiber. And so it's the time that takes the mirrors to align to the proper fiber, to steer the beam to the proper fiber, that determine the speed at which the rerouting occurs. Okay? And so here is one of those systems. You see that they are massive. Those systems are deployed in the field. They are quite effective. And what is very important in this deployment is the fact that the losses, okay, how much power you lose from going from here to there is essentially negligible, okay? And so those are very effective. They are costly because each one of these router here, it costs a few 10,000 euro, $10,000. And therefore, so we were motivated to try to use silicon photonics in order to replace one of those routers. And so this was a European project where we were involved in. And so there were many partners, so ST Microelectronics, Ericsson, and the foundry in Grenoble, and then even a Korean partner. And the objective of this project was to develop what is called an integrated transponder aggregator. So here the idea is to have something that is able to send therefore change the configuration in any direction. So it can be use any wavelength and can avoid to have contention on the circuit. So the overall objective was to make one very compact circuitry where you have a certain number of input optical fiber, in this example 12 optical fibers, that do define 4 different optical channels by using a given spacing between the different channels of 100 gigahertz and be able to send the signal along the standard 4 directions, so north-south, west-east. And then, in addition to that, what you want to do is that you want to add or drop up to 12 channels from the router. Everything should be done by being able to produce the system with a low cost, instead of 1,100 euros, with a very small form factor, and at a speed of a few microseconds. Okay? So those were the objective of the project. And so in order to make a router, you need to have a switching element. So a single element that is able to switch the signal from one direction to another direction. And so the switching element were the silicon microresonator. And here the idea was to have an array of silicon microresonator by which we are able to switch the channel from a direction, so for example here from the input to the through, or to another direction, for example here from the input to the drop. Okay? So then this switching mechanism can be implemented in a matrix of ring resonator, and depending on the color of the light, so depending on the wavelength of the light, depending on the status of the microring resonator, what you can do, you can decide to have your light signal that is going through and then is switched in this direction, or depending on the wavelength of the light, so the signal is going through and is switched in this other direction. or, depending on the color of the light is going through without being switched. Okay? So this is the principle that we want to exploit. A matrix of ring resonator, each one individually addressed in order to control the direction where the light is propagating. Okay? So this is the earth of the system. But then you have to implement this system into an architecture. And so this is the actual architecture that we have fabricated. Okay? So the architecture is quite complicated. So let me go through step by step in each one of these elements. So at the end, at the input, we have the 4 directions. So our optical signal is coming from 4 directions: north, south, east, west. And then is inserted into the switch of arrays of microring in the array of microring resonator. Oh, sorry, my phone. In the matrix of microring resonator, I should turn off the telephone. I forgot. Okay, where is the telephone? So you see that now is working time in Italy, so it's about 8 o'clock, 8:30, so people start to go. Anyway, so you have, and so here you have the matrix of microring resonator. However, you have a first point that you need to have to separate the different wavelengths that are coming from the input. And therefore, you need to have here a demultiplexer that is demultiplexing the wavelength. I'm going step by step later on the different functions. So then you have your matrix of microring resonator, and then here you have the drop port. So let us assume that you want to send a channel, so a wavelength from this input here to that drop port. Okay? And therefore, so your microring resonator should be able to select the proper wavelength from the proper input port and send to the proper drop port. And so in this way, so you perform the action of dropping a channel from the network. On the other side, the microring resonator should be also do the opposite function. Therefore, so what you have to do is that you have to have the possibility to add a wavelength to a given direction. Okay? And so this is the add function. And so we have to implement our system in order to be able to, on one side, add, on the other side, drop any wavelength from any direction. And so this is the kind of function that we want to implement in this specific circuit. And so what we did was to design a proper circuit. Okay, let us concentrate on the single input. Okay, so we have one direction. Okay, here we have a grating coupler, and so by using this grating coupler, we get the signal coming from the fiber. So on the single fiber, we have up to 12 different wavelengths that are traveling, and so we need to have here the grating that is able to couple any of those 12 different wavelengths to the input line. And then here, there is the first function that we have implemented, a function that is called an interleaver. I will tell you what an interleaver is in a while. Then after the interleaver, we have a demultiplexer stage, meaning a stage which is able to route all the different wavelengths, so the 12 wavelengths, into the different waveguides, which are into the different rows of our matrix. Switching matrix. And therefore, so this is the demultiplexer. And by using this demultiplexer, now we have that lambda 1 is going in this row, lambda 3 is going in that row, and so on and so forth. And so we have demultiplexed the input wavelength along the different row of our matrix. And notice here that we have two demultiplexer, one for the odd wavelength and the other for the even wavelength. And this function to separate the even from the odd wavelength is performed by the interleaver. Okay? So the interleaver is a component that is able to separate the even from the odd wavelength. And then we have the demultiplexer. So the demultiplexer, what it's doing is that is channel the different wavelength along the appropriate rows. Then what we have the switching node that are our head drop microring resonator that should be tuned in order to determine whether this wavelength should go through or should be dropped from the switching matrix. Okay? And therefore now we need to understand the working function and see how we have implemented all those different functionalities. So the interleaver, the demultiplexer, and the switching node. In addition, here we have other components that are crucial to be understood. You see here that in this point we have a crossing between a wavelength and another wavelength. So in the matrix we have many of those crossings where two wavelengths cross. And so we need to understand what is happening at the light signal in correspondence of those crossings. Okay? So these are the toolbooks that we have to be able to implement in this integrated circuit. A crosses that should be characterized by a very low losses because we have many of those crosses, and should be compact because otherwise we need to have a full wafer for making our network. Then we need to have this interleaver, and so the interleaver is the device that is able to separate the odd from the even wavelength. And this separation should be done without losing any power and with having a very good channel rejection. So channel rejection means that we do not want to have any even wavelength where the odd wavelength are. Okay? And so the channel rejection should be larger than 20 dBs. And so what you see here is the fact that when you are designing those components, so you have some design parameter that your design should satisfy. And this is what we need to satisfy. So we need to satisfy that our circuit has a design that is able to perform the functionality of separate the wavelength with a channel rejection of 20 dBs. Okay, the separation should be as good as having only a residual fraction of the initial power in the wrong channel of 20 dB. Then we have the demultiplexer. The demultiplexer should be able to demultiplex, separate the single input waveguide where we have the 12 wavelength into 12 different waveguides. Okay, so we demultiplex the signal from a waveguide to 12 waveguide. And this demultiplexing is based on the wavelength of the light. Okay, so lambda 1 should go to the first waveguide and lambda 12 to the last waveguide. And even here, so we need to have a very good channel rejection, meaning that the residual power of lambda 12 on the first waveguide should be lower than 30 dBs. Okay? And so those are also parameters that we need to satisfy in our design. And then we have the switch. The switch are the microring resonator. And so here you see the free spectral range. So the separation between the different resonances should be larger than 2.4 terahertz. Why this so spaced? So the reason is that we have a comb of frequency, a comb of wavelength, and we want that this comb of wavelength should be allocated within a single free spectral range. And so this means that the resonance, the two resonances of a ring, should be separated by this quantity. The reason is simple. So here I have lambda 1. Here I have lambda 12. Okay? I want that the switch should operate on lambda 1, and the same switch should not operate on lambda 12. However, if I have that my resonance is this one, and this one, and so this is the free spectral range, you see that while I'm moving this resonance here, also that resonance is moving. But this resonance is moving in a wavelength region where I have lambda 12. And therefore it happens that the same microring is routing this lambda 1, but is also affecting the routing of lambda 12. And I want to avoid this. And in order to avoid this, I need to have a free spectral range that is larger than the overall span of my lambdas. Meaning that I want to have a free spectral range that is something like that. Okay? In this way, I'm sure that when I'm moving this resonance here, I'm not affecting lambda 12. Okay? And this is the reason why I want to have a free spectral range that the free spectral range is the reason why I want to have a free spectral range that is larger enough, where is here, is larger enough in order to accommodate all the different lambdas. Okay? And then clearly in my switches, I want to have low losses. I want to have low power consumption while I'm switching. And I also want to have a very good isolation, meaning that if I'm operating on lambda 1, nothing happens to the other lambdas. And so this is what I do want to do. So then those toll books need to be implemented in my overall switch I have already described here. And so let us start, okay? So in the switch, so the first component is the grating. And here is the grating coupler that we have developed. So this is simple, no? The grating coupler, so you have, so the reason, anyone can guess why the grating coupler has this triangular reason? I could do a grating coupler with a square. I can do something which is like that. So instead of doing that, so here in the design, so what we did was something like that. Why? Exactly. The first is the tapering. So here we have an adiabatic tapering. So the mode from there goes to here without any loss of power. Instead here, so we have that the mode is so large that all the power here will be lost. But the second reason, the second point is that you see that here, so the lines, so the grating are not vertical, but they are curved. Why? Good. Partially good, the answer. So those who have glasses should know. Why the surface of our glass is not flat, but is rounded? We are imaging, right? And so this is the same. So here what we are doing is that we are focusing the light by the grating in this point here, exactly. And so during the optimization, during the design, I know that you are doing some design in your courses. So those are aspects that you need to take care of. So you want to optimize the quantity of light that is reaching the waveguide here. And therefore, so you have to optimize the shaping, so the curvature here in order to focus the light there, as well as you want to avoid to have any loss in this part here of the grating. And therefore, so you have to carefully design the tapering. Anyway, so then the gratings, so this is the actual grating, so this is schematics. So the grating has been done, easy, no problem, so we know how to do. Then the second function is the separation. So what we want to do is that we want to separate the odd from the even wavelength. And so in order to do that, we use this device that is called an interleaver. And in this case, it's nothing else than a Mach-Zehnder interferometer loaded by a micro-ring resonator. So this is the interleaver, okay? So here is the actual design of the actual realization of the interleaver. Here you have an MMI, an input splitter, and so the light is split into two different arms, so one here and the second there. And then here you have another MMI, so where the light is recombined, so this is a combiner. And therefore you have that half of the light, half of the wavelength are going to this channel here, and half of the wavelength are going on the other channel there. And so the design is done in such a way that depending on the input wavelength, so you have that the light is going to the bar or is going to the cross direction, okay? So this is simply using the dispersion, the refractive index dependence on the wavelength and the appropriate design so that the free spectral range of the Mach-Zehnder interferometer is exactly equal to the separation between the two different wavelengths, okay? And therefore, so what you end up is that the blue, okay, so the even wavelengths are channeled in the cross direction, and the dark blue, which are the odd wavelength, are channeled in the bar direction. So now, by using this device, you are able to separate all the different channels depending whether they are even or odd. Okay? And so here is quite well performing. You see that the inputs, so those are experimental measurements. You see that the inputs the input losses are only 1 dB or less than 1 dB. So then you have achieved this function. And then let's go to the next function. So the next function that is also very important is the demultiplexing. And so in order to demultiplex the light channels, what we are using is what is called an array waveguide grating. The array waveguide grating is working exactly as a prism. Okay? So in a prism, you have that the white light is entering, and then you have that the light is refracted along the different direction depending on the color of the light. Here you have the same function implemented into an integrated circuit. How does it work? So it works in this way. So we have the input waveguide where the white signal is coming. Then you have a free propagation region. So here the light is exiting from the waveguide and then is spreading in a planar waveguide in such a way that, and this is carefully designed, in such a way that is illuminating with the same intensity all the output waveguides that you have here. And all these output waveguides are those that constitute the arrayed waveguide system. Okay? And then what you have here, you have a central part where each one of these waveguides has a length difference with respect to the nearby waveguide. So here you are increasing the length of the waveguide by a given length. So this increase in the length causes a different phase shift between the light that is traveling along all those different waveguides. Okay? And this difference in the phase is behaving like a grating. And therefore, this system behaves as a dispersion grating. Meaning what? Meaning that at the output here, you have that the different color of the lights are directed in different direction. So, for example, if you have, what is here? If you have red line, so what you end up is that depending on the wavelength, the phase shift is different, and therefore here you have all the light with red color that is coming. They are focused on this specific point, and here you get constructive interference of the red light. But then, if instead in the input you have a green line, what happens is the fact that this green line suffers a different phase shift, and therefore the constructive interference condition for the green light is in this other point here. And therefore, by using simply this length difference, you are able to address, as a function of the wavelength of the light to this output port or to this other output port. And therefore, in this way, what we are doing is that you are demultiplexing the white light along different output waveguides. Okay? So this is something that you can design. It's quite easily, so the parameters are standard, and you can build your system. And here is an example of what we have done. Where is it? And here is an example of what we have done. Okay? So this is indeed the construction of our array waveguide grating, short AWG, which is behaving as a demultiplexer. And what we are doing here is that we are sending a signal at the input, and then we are changing the wavelength of the signal at the input. And then we are collecting the signal at a single waveguide output. And in this case, so we are collecting the signal here. And what you see is that depending on the wavelength, we have minus 40 dB of output, so a negligible signal. And then at this specific wavelength, so we have a peak in the output. So that means that when we enter with any wavelength from this input there, at this output here, we only get the light that has this wavelength there. So then we change the output waveguide, and this is what we are measuring. So we change the output waveguide, and this is what we are measuring. So we change the output waveguide, and this is what we are measuring. So what we get is that depending on the color of the light, so we get that the output waveguide is changed. Okay, so this waveguide here is getting the violet light. This waveguide there is getting the yellow light. This waveguide here is getting the red light. And this waveguide there is getting the blue light. And so we are able, by using this simple device, to demultiplex the input light. Okay? And in this case, you see that the channel crosstalk, so how much of the blue light is going in the light blue signal is negligible, so it's only 30 dBs, while in the nearby channel you have that of the blue light in the nearby channel you have only minus 15 dBs. So you have a good channel-to-channel isolation. Then we have another function to perform, that is the routing. Okay, so once we have the multiplexed, so we have reached our micro-ring resonator, and now we need to design the single node. And here is the design of the single node. So initially, so what we were thinking was to use a single micro-ring resonator. So 10 micron in diameter, the micro-ring resonator, and the blue line here is the transmission of the micro-ring resonator. What is the problem with a single micro-ring resonator? The problem is that we want to manipulate this given channel, so this given wavelength, but however, the light that is transmitted by the micro-ring resonator in nearby channel is too large. Okay? So in order to increase the rejection rate, so in order to decrease the quantity that adjacent channels, so different wavelength channels, are affecting the proper channel that we are addressing, so in order to decrease this, what we end up was a sequence of two micro-ring resonator. So now the idea is to have a light that is coming here, is coupled to this microring resonator, is coupled to this other microring resonator, and is exiting there. Okay? So we can implement the same add drop function instead of using one ring resonator, using two ring resonator. What is the outcome of using two ring resonator? So the first one is that we reduce significantly the crosstalk, so we increase the isolation, as well as we have a transmission of the two ring resonator, which has a flat top, a flat top shape, meaning that we are not deforming the light signal that is propagating in the desired channel. Then, in order to switch the channel, so in order to trim the actual channel that we are working on, so we place ether on top of the two microring resonator. And then we demonstrated that it is indeed possible to tune the resonance position by simply injecting current, so by simply powering the single microring resonator. And what you see here is the fact that you have a consumption for the microring resonator of only 20 milliwatt, very low consumption, and then the speed at which you can tune the microring resonator is 4 microseconds. Compared to the millisecond in the MEMS approach, so you see that we have obtained a very significant improvement. So the other issue here is about how do we optimize the transmission of, so the other issue is about the fact, so, no, this is the optimization, correct. So the other issue is how do we optimize the single microring resonator spectral position. I have already told you that once you fabricate the microring resonator, the fact that you use a lithography of with a resolution of 5 nanometer, cause that the actual position of the microring resonator is slightly different one with respect to the other. And this, the black line here is, in case of having a channel with 4 different microring resonator, is the transmission of this system. And so what you see here is the fact that the actual spectral position of this microring resonator is slightly different from the actual spectral position of this other microring resonator, that is slightly different from the third microring resonator spectral position, even though nominally they are all equal. From the design point of view, so they have all the very same radius, 10 micron of radius. But then the actual fabrication caused by the finite resolution of the lithography caused that the spectral position of each one of those is slightly different. And therefore, this is something that we cannot accept, because in our matrix we have 100 of those microring resonators. And so what we need to do is that we need to very carefully align all those microring resonators. How can we do that? Well, we can do by using the ethers. And so now, so what we do is that we inject a proper current in each one of those microring resonators so that to be able to align all the microring resonators to the same wavelength. And this is the outcome. Okay? So you see now that we were able to align all those microring resonators together. Then there is another practical point of view. So the thermal crosstalk. So let us assume that we have many of those microring resonators, and then what happens is that we want to hit one of these microring resonators because we want to move the spectral position of that microring resonator. So the question is the heating of that specific microring resonator affecting the others or not? If the heating is affecting the others, means that we want to switch one node of the matrix, and indeed we are switching all the nodes around this single node. And this is an effect that is called thermal crosstalk, meaning that we want to hit this node and we are hitting also the other node around. And this we want to avoid. And therefore, so what we did was to do a a modeling of the heat flow of the temperature rise inside the microring resonators in order to be able to space the microring resonator at a proper distance so that the thermal crosstalk is completely negligible. And so this analysis was done in Korea. So here is the model, and these are the results. So let us assume that now we are heating this microring resonator. And so what we see is that we can, depending on the current that we are injecting, so we are changing the temperature of that specific microring resonator. So in this case, so we are injecting a current up to, which is up to 200 Kelvin, the microring resonator. So now you also see the kind of temperature that you achieve. So you are injecting 20 milliwatt of optical power, and the local heating of the microring resonator is up to 200 Kelvin. So you are heating quite much. But what is nice here is the fact that now, if you look at the nearby position, you see that the temperature rise of the microring resonator nearby is negligible, less than half of Kelvin. And therefore, so what you get is you get a very fine tuning of the distance, which reduce at zero the crosstalk. For example, this one is the temperature increase of all those nearby microring resonator when we are operating this microring resonator, as well as when we are operating this other microring resonator. And what you see is that the temperature rise depends on the specific microring nearby that you are controlling, but is always less than 1 degree Kelvin. And so the shift is negligible. And so in this way, so we have optimized the function of the node, as well as the spacing of the different nodes on the circuit. Then another function that should be optimized, quite carefully optimized, is the crossing. You see in the matrix how many crosses we have, 100 of those crossing. Consider that each cross could have a loss of 1 dB. It means that on the circuit we will have 100 dB of loss, which is unacceptable. And therefore, one has to carefully design the crossing. So crossings are very important in photonic circuits. And here is the kind of design that reduce the insertion losses to less than minus 0.02, minus 0.04 dB over the full spectral range of our different channels. How can we optimize that? We use the concept of self-imaging. So the idea is to carefully design the free propagation region here in such a way that in the crossing you get that the image of the input port is reproduced at the cross point here as well as in the output port. You have a free propagation of the light, like having a lens in between. And so you have that the light is collected and then is focused and then is expanding and then is refocused. And by optimizing the length and the width of this free propagating region, you are able to focus the light exactly in the center. Focusing the light there means that you do not have any light that is going in this direction or in that direction. So that means that the crosstalk, so the amount of light that is going in this direction, that is the unwanted direction, so is lower than 45 dBs, so negligible. And so essentially you have that your light is passing the cross without loss as well as without any contamination of the other direction. And so in this way, so we have implemented a quite effective cross on a very small footprint, 10 micron. Then what we have also implemented in the circuit were the monitor photodiodes. So clearly you want to know what is happening on your circuit. And therefore, you have to implement some monitor photodiodes that tells you how much is the power that is reaching there and how much is the power that is reached the other direction. And so what we did was to use this kind of configuration for the monitor photodiode. So here the advantage is the fact that on one side, so you control the coupling here, very small coupling because you do not want to remove too much power from the line. So very small coupling factor here, and then you have a looped waveguide so that you can monitor both the signal that is coming here is coupled and then is reaching the photodiode, or the signal that is coming there is coupled and then is reached the photodiode. Okay? So this is a bidirectional monitor of the light that is propagating in the specific point of the waveguide. And you do that by integrating heterogeneously integrated germanium. Okay? This is something that I have already shown you yesterday. So then all the different functions can be realized. So now you can build your matrix, your switch matrix, which has more than 1,000 components. And then you need to integrate an electronic block that is able to address, to inject or extract the signal from all these components. And so we did also, this was done at University of Vienna, Technology University in Vienna. So we need also the design of an ASIC circuit, which was able to, on one side, collect the current from the monitor photodiode, and on the other side, provide the proper current to the heating resistor. Okay? And so now what we have to do, then the logic to the address logic in order to know which one of the specific microring resonator you have to address. And therefore, so then we do this design. And so what we did was that we designed on the electronic integrated circuit, operational amplifier, transistor, in order to be able to inject the proper current in the voltage heater. Okay, so this is what we did. And then we start to build up. So this is the architecture, so the sequence of processing steps into which we fabricated the micro ring in the photonic integrated circuit, then the germanium photodetector, then the heater on top of the micro rings. Then we open the vias in order to insert the metal lines to contact the heater or to contact the P and N side of the germanium detector. And then we bond on top of the photonic integrated circuit, the electronic integrated circuit. We also open the space in order to allocate the fiber. And then this is the architecture that was then transferred into a specific photonic integrated circuit design. So this is the actual mask that we designed for the foundry. And what you see here in the mask are the pads, the metal pad for the metal wires. And then you see the matrix of micro ring resonator, which is the switches element. And then here you see all the input and output gratings. And what you realize, or at least I hope you realize, is the space that the input and output gratings takes in your design. So you have a lot of space that is only used in order to handle the input and output gratings. You know why we need so much space here? For the packaging. The fibers are 125 microns in diameter. And therefore, here you need to have 125 microns in order to put all those different fibers. So the fibers are taking a lot of space. Anyway, so this is the actual design. Then the design was transferred to the foundry in Grenoble. And they indeed produce 200 millimeter wafers. And on top of these 200 millimeter wafers, you have all the single dies that are the single switching matrix. And this is the actual chip fabricated before, before bonding. Here you see the gratings, the different gratings. So you need to have 4 gratings for the direction and 12 gratings for the add drop channels. Then here you see all the different microring, double microring resonator-based switchers. Here you see the demultiplexer, the AWG. Here you see the interleavers. In the output you have again the interleavers. And then here you have the, I don't know what you have here. So you have something there. Because the waveguide is going from here to there. So all the input as well as output waveguides are going there. And then you have here all the metal lines that are used in order to insert and extract the electrical signal from the circuit. Then on the other side, you have the electronic integrated circuit. And this is the electronic integrated circuit with all the different functionalities, as well as the input-output electrical channels. And then what you do is that you place the electronic integrated circuit on top of your photonic integrated circuit, and then you place here the fiber array that is used in order to insert and extract the light signal from the circuit. And then you see that the metal wires touch the photonic integrated circuit, and then here you have electrical wires that takes your input and output signal from here to the electronic integrated circuit. And in order to couple the electronic integrated circuit to the photonic integrated circuit, we use this technique that is called the technique based on the copper pillar. So you have a copper pillar that is placed on the electronic integrated circuit. So all the signal from the electronic integrated circuit reach this coupled pillar. And then you have a tin base solder that is used in order to solder to bond the electronic integrated circuit into the photonic integrated circuit. So at each node, at each point, contact point, you have one of these bumps, which is physically pressed at high temperature with the same configuration you have on the photonic integrated circuit in order to make an electrical contact. And now the signal that is processed by the electronic integrated circuit can travel through this contact and reach the thermaliter or the photodiode. So this is the result of the bonding between the electronic integrated circuit and the photonic integrated circuit. So the bonding is quite effective, is quite compact. And then what you do is that you bond also the optical fibers. And so those are the optical fibers that are reaching this fiber array. So here you have 20 fibers. And those 20 fibers then are carefully coupled to the photonic integrated circuit. Everything is glued together and can be placed into a package. So I have already shown you this package. And so the package has the function of hosting the optical switch matrix here, having input fibers, having input electronic digital signal, and then controlling the temperature that is developed in the circuitry. Everything is placed in a board. So here you have all the different fibers. Here inside you have your optical network. And here you have some microprocessors that are used in order to address the different routing protocol that you want to implement. And then you take the circuit and you take the circuit to the lab where you have the circuit, you have a tunable laser that provides you the input optical signal, and then you have a photodetector that allows you to measure what is coming through your optical network. And then you hope to have a very bright PhD student that can do the testing. You do the testing, and these are the results. And so here is the node that you want to test. So you have an input, then you have an interleaver, then you have a direction, and then you have to switch the proper wavelength where you have a multiplexer, you have another interleaver, and then you have the output. And so you start. You connect your laser to the input, you tune the wavelength, and you try to address the switching of this color to the output. And then you start to do the measurements. So the first measurements is the grating coupler. So you measure the amount of light that is transmitted into the circuit, the photonic integrated circuit. And so this, what you see here is the measurements of the grating loss over the Wolf wavelength region that you are interested in. So you see that the grating loss are quite flat. So then you can move, and then what you measure is the transmission from the interleaver. And you see that in the interleaver, so you are able to separate the odd from the even channels, the odd from the even channels, and so on and so forth. So the interleaver is working as it is desired. And then you are actuating the switch, and you are measuring whether the switch is able to switch the proper channel. And what you see here is the fact that after the switch, instead of having all those channels going through, you have only one channel that is switched off. Okay? And so in this way, so you are able to address exactly this wavelength color to this output. Then you have the multiplexer that is taking the signal here and then is multiplexing the signal to the output. And then you have the action of the second interleaver here that is remixing all the different, the odd and even channels. And then finally you have what you are measuring on your output photodetector. And so here what you measure is how much of the power that you have inserted into added into the optical network is effectively added to the channel, to the direction that you want to address. What can you say of this result? Any comments here? So is the switching working or not? Yes, it is working. No. So we want to send this blue light there, and indeed, so we are able to send this blue light there. But here there is an issue. What is the issue? Looks at the number here. Yeah, power losses, minus 20 dB. So it means that we are losing 20 dB of the input optical power. That is huge. But let's see if we can work on another channel. So here is what we did with another channel. Now we want to switch the blue light. And so we insert the blue light, so the blue light is going, and indeed we get the blue light. So the performance are quite uniform because you see that we have the same losses on the blue than on the red line. The performance is also good in terms of rejection of nearby channels, minus 50 dB. But still we have... Perché non si vede questa? Okay. But still we have that, so this is fancy, okay, but you can see. You see that we are able to send in the output add in the output direction all the required different 24 wavelengths, but still with some losses. So the losses are really an issue. So then we try to see whether we are indeed able to put this transceiver on a traffic line. And so here is a traffic actual a diagram of the switching working with 20 gigabit per second input wavelength. So you see that the I diagram before and after having added or dropped a channel from the line, so the I diagram is open. Even you can look at the bare test, so bit error test, and you see that you do not add any significant penalty by using the optical switch. So everything looks like that it's work. You also have a very negligible contribution by interferer. So from the point of view of the networking application, so the switch is quite well working. From the point of view of the functionality, the switch is actually working, it satisfies all the requirements. Here the problem is the fact that we are using silicon, and silicon is a passive device. Meaning a passive device, meaning that in this case, so we still have 20 dB of losses. And where those losses come from? Most of the losses are coming from the input, from the grating losses. You see that we have 5 dB of grating losses. Okay? So the grating losses is still too huge in order to be accommodated in our system. So we have 5 dB in the grating losses. Then the other losses are associated to the switch. Okay, the single switch, you see here that we are adding from here to there. By simply switching the channel, we are adding 4 dBs. So we have 10 dBs from the gratings, 4 dB from the switches. That makes overall 14 dBs. It's too much. Okay? And this is the reason why this project was ended. Okay? So Ericsson, ST, Microelectronics say, yeah, that's fantastic because you can switch at a microsecond time scale, but then you are losing too much power. How can we solve this problem? Any idea? You see the problem, no? We lose too much power. How can we solve? Say? Who was saying? With an amplifier, clearly. So the only solution here is to put on the chip an amplifier. So using SOA integrated in the circuitry. Okay. However, if you use an SOA, what is the consequence? Yeah, but the size is not a big issue. No, that's not a problem. We show that we can integrate 3.5 on silicon. So we can make laser or whatever. What is the problem of having an amplifier? Exactly. So the problem of the power amplifier is that you increase the power consumption of the device. And therefore, so there is a trade-off between the power consumption that you can accept and the integration and the losses that you can accept on the line. Okay. Therefore, but our problem in that specific program was the fact that in order to integrate the 3.5, so the SOA, so we have to start another project. And the funding agency has not given us the money to do that. And so therefore, so we finish. So I hope to have shown you actually so the sequence of paths through which we were going in order to get those optical switch and integrated optical network working. So if you are interested, here is a list of papers that we wrote about that project roughly 5 years ago. So that project was run. And clearly this project was only possible because of this initiative that Europe is supporting of collaboration between different multiple institutions. So in this specific project, we have institutions coming from Italy. We had institutions coming from France. We had institutions coming from Spain. We have institutions coming from Austria. We had institutions coming from Sweden, as well as we had a collaboration with a South Korean institute center. Okay, here I have finished. Other question? Any question? So if not, I think that we can close. We can go to have our lunch. In time, this time.
So as we have to proceed for the group photo and the meeting with the Honorable Director, sir, so we are proceeding ahead. You all can come there. Okay, and after that we'll have lunch here from 1:30. Okay. Yeah, first the photo, then the match.
First the important things.
Yes. First the important thing, the proof. The main building, you know. All of you, all the participants, please, आप लोग, you come on your way. ठीक है? We'll go ahead. तुम लोग लेके आ जाओ. statue के पीछे इस तरफ है ना. Statue is that side. I'm telling this side. That side. पीछे से जो है stairs are. Where did you get these prints? The printouts.
Yeah, I did.
So you came full prepared.
Yeah, I am prepared.
Sir, it will be very hot. Sure, you like to wear the jacket and this? Yeah, that is good. What happens in Indian wedding? You always have to wear, getting married. It's very hot in me. Like sweating and all that.
So maybe this one I can. Ah, no, because then.
Then we again
Yeah.
give it to temperature.
Please follow us, otherwise we will be left outside of the department. Then from there we will get right, and immediately we will get. So this is called main academic building backside. Okay. We can keep the bags here, no problem. We will just have a photo, then we will come back for lunch here only.
Keep your IDs.
Keep your IDs because that is required.
For the photo.
Bag मत ले जाइए, luggage unnecessary you will be carrying. तो आपने बताया नहीं था, मैं तो एसी का भी रिमोट कंट्रोल भी नहीं था।
अभी मैं बंद करवा देता हूँ। नहीं, बंद नहीं करवाते ना। ऐसे सब लोग आएंगे। ये प्रदीप है नहीं। आप छोड़ दीजिए, सब बंद हो जाएगा। गेट वेट बंद करके